Hello friends, welcome back to You Can Do TV. $30 million tons of rock get torn up every year at one mine to produce 8 million tons of iron pellets, 22 million tons of iron pellets. Then those pellets travel across oceans, get poured into furnaces at 4,000 degrees Fahrenheit, and come out as steel coils at thousands of feet long. Watch to the finish, and the strangest twist about this whole industry hits you. These little brown balls rolling off the conveyor look like something you would find in a fish tank. They are not. Each one is a taconite pellet, roughly 65 to 66% iron, and every single one is the reason entire mountains get rearranged somewhere else. The mining operation feeding this line runs across nearly 7 miles of open pit in northern Minnesota. Around 185,000 long tons of material move through the pit every day. Only a fraction of that ever becomes a pellet. The rest is rock that had to be blasted, hulled, crushed, and separated out just to isolate the iron hiding inside. Explosive charges loosen more than 1 million tons of ground per blast, the kind of noise that would clear a real estate showing 3 counties away. Electric shovels scoop nearly 60 tons per bite. Haul trucks the height of a 2-story building creep away with 240-ton payloads. At the plant, gyratory crushers reduce the rock, autogenous mills grind it into slurry, and magnetic separators pull the iron out grain by grain. Around 30 million tons of rock come in a year to make 8 million tons of pellets. The other 22 million rejected. Every pellet is what is left after the mountain lost the argument. Meanwhile, in the Pilbara Desert, an autonomous train, no driver, no snack breaks, no country music playlist, hauled its first load of iron ore across hundreds of kilometers. One of the world's biggest robots, essentially, moving one small ingredient in a chain. And it starts with rocks in the ground. Every iron ore region on the planet grew up speaking its own dialect, its own equipment, rock chemistry, and opinion on what counts as a bad day. In northern Minnesota, everything revolves around taconite. This pit near Chisholm shows the ingredients up close. Terrace walls stepping down into the ground, haul trucks the size of small buildings crawling along benches like very expensive ants, a drag line swinging its bucket into the wall, and a conveyor belt shuttling crushed rock to the processing plant. The drag line alone moves truckload after truckload without stopping, feeding a system that pretty much refuses to sleep. Step back from the pit and Minnesota's whole iron range starts to make sense. The rock here is around 30% iron, hard flint, like taconite deposited about 1.8 billion years ago, long before anything with a spine walked the earth. Before a shovel touches the ground, permits and environmental reviews take years. The mine operator has to promise in writing how the land will look once the ore runs out. Anyone here worked reclamation on a mine site? We'd love to hear your take. Not every mine gets away with just crushing rock and shipping it. A serious magnetite project needs its own concentrator, worker village, private rail line, and dedicated port loader, the sort of shopping list that turns bankers pale and construction schedules into multi-year commitments. Head across to South Australia, and yet another version shows up. The Middleback Ranges have been mined for hematite since the late 1800s. Today, the operation pulls more than 6 million tons a year from active pits, feeds part of it through crushers and screens for direct export, and pumps the magnetite fraction through underground pipelines to a nearby pelletizing plant. Cape-sized vessels, 170,000-ton, floating giants get loaded 8 nautical miles offshore because the ships are literally too big to fit inside the port. The port apologized. The ships did not care. And here's the technical fork every mining region hits sooner or later. Iron ore mostly shows up as either hematite or magnetite. Hematite runs high grade at 56 to 62% iron and ships straight after crushing. Magnetite starts lower grade in the ground, but magnetic processing lifts it to 65 to 70% iron. Taconite falls into the second camp, a lean, silica-heavy rock, written off for decades until the rich hematite reserves started running dry. Man, picture, the geologists told for 40 years the rock under their feet was worthless, then watching the industry come sprinting back. Raw magnetite is still nowhere near ready for a blast furnace. The iron grains are locked inside stone, and prying them loose is where the real work begins. Meet the plant whose entire job is to remove everything you did not order. The feed here shows up at around 45% iron, respectable, but not the grade a steel mill will hand over premium cash for. The plant runs the material through crushers and screens, splits it into size fractions, then sends each fraction past a series of high-intensity roll magnets running between 1.1 and 1.5 Tesla. Magnetic material peels off toward one belt. Tailings drop away toward another. Same rock going in, but the exit price gets a serious promotion. The finished product leaves at roughly 58% iron. Then there is the plant built specifically to turn a waste pile into revenue. For years, low-grade hematite too poor to sell was piled up beside the mine, the industrial equivalent of leftovers you keep meaning to throw out but never do. Turns out procrastination pays. This 700-ton per hour wash plant takes those old stockpiles and pushes them through a full beneficiation circuit designed to remove silica and alumina from extremely abrasive rock. Front-end loaders feed raw material in. Scrubbing units break clay off the ore. Jig gravity separators split heavy iron-rich particles from lighter waste. Spirals do a second pass on the finer material. Water gets recycled through the plant, and the finished product stockpiles cleanly on the outbound conveyor. The feed lands at 43 to 52% iron. The output, over 60%. A waste pile just quietly became premium-grade concentrate. And when the ore particles are already ground finer than beach sand, the whole approach shifts to wet magnetic drums. Slurry pours across a rotating drum with a magnet inside. Magnetite grains cling to the surface like they owe it money. Everything else washes away. 3 stages take the feed from 35% all the way to 64%. Now put the whole idea into one plant at real scale, out in Central Asia. The raw feed lands at 360 tons per hour, sized up to 600 millimeters, running around 34% iron. Multi-stage crushing knocks the rock down. Screens sort by size. A specialty ore against ore separator handles the final stage and lifts the product to 54% iron. A 20-point jump in iron content is the line between a mine that eats steak and one that shuts down. The answer is not more trucks. It is a pipeline. Ore concentrate gets mixed with water into a thick reddish slurry, then pumped through steel pipes across forests, hills, and state lines. Fine ore powder alone will not stick to itself. Roll it around all day and you get more powder, the industrial equivalent of trying to make a snowman out of dust. Every pelletizing plant relies on binders, additives that let mineral grains grip each other long enough to form a ball. Modern organic binders can even replace part of the traditional clay binder. Step inside a working plant and the machinery finally makes sense. Conveyor belts run for hundreds of meters. A rotary kiln towers over the yard. Every belt, chute, and blender is there for one job. And here is the machine that actually shapes them. A giant inclined disc rotates slowly, letting damp ore powder tumble across its surface. Small particles snowball into larger ones. A camera watches the process. Target size is 10 to 14 millimeters. A pellet the wrong size chokes a blast furnace faster than bad merger news. Wet green balls roll off the disc, get screened, then head into a rotary kiln to harden at high temperature. Compared to raw lump ore, pellets boost sponge iron output, roughly 50% finer output, roughly 50%. Holy smokes, half the world's steel now runs on these little brown marbles. Watch a 1,000-foot laker glide up to the pier at Marquette, and it looks almost peaceful. It is not. Every hatch on the deck is already open, and 62,400 tons of empty capacity is about to be filled with iron ore pellets that fell straight from the dock above, no cranes required. Now pull the camera up and the trick becomes obvious. The whole dock is elevated. Pellets ride ore trains straight to the top, drop into storage pockets, and slide out through gravity gates directly into the ship's hold. The pier does the work. The tugboat gets the applause. Step inside a laker, and the just fill it up idea falls apart fast. Load lights and draft gauges get watched every second. Hit the balance wrong, and the hull develops a hog or a sag. Anyone worked a bulk carrier crew. Hog and sag near misses must have some real stories. Drop one below. Push the whole process into time-lapse, and the ore highway of North America finally reveals itself. Trains roll in from the mines. Hatches on the deck slide open. Storage pockets above the ship let material drop by gravity straight through the hull openings. Every few minutes, a new load thumps down into the hold. Dust kicks up, and the ship sinks a little deeper into the water. A 1,000-foot vessel fills in hours instead of days, then peels away toward the next steelmaking town on the lakes. Cargo trucks would take weeks to move what one ship carries in one trip. Meet a private port built for exactly one thing: sending Brazilian iron ore across the ocean at industrial pace. Trains arrive from the Iron Quadrangle carrying 134 cars at a time. 2 car dumpers empty a full train in about 3 hours. Conveyors then run through an 1,800-meter tunnel to the pier, where 50-meter-tall ship loaders fill Cape-size vessels at 12,000 tons per hour each. The whole facility is the industrial equivalent of a fire hose pointed at a boat. Head over to India's east coast, and the numbers keep climbing. 3 tipplers empty up to 16 railway rakes a day. Ore travels along a 2.5-kilometer receiving conveyor, gets stacked across 30 acres of yard, then reclaimed onto a 6.7-kilometer shipping conveyor that leads to a shiploader running 8,000 tons per hour. What really matters here is what you do not see. Zero dust emissions, zero spillage. For a facility moving mountains of ore, that is genuinely rare. And this is where a real trick shows up. Ore from different mines gets dosed with limestone and anthracite, ground, homogenized, filtered, and heat-treated right at the port. Same mine, different customers, different chemistry in the ship. Nobody in Osaka is buying the exact same blend as Rotterdam. Down in Peru, another version of the same idea. A fully enclosed terminal receives 150 to 200 trucks a day, plus rail cars, weighs and samples every load, stores 500,000 tons under cover, and loads ships automatically. Iron content gets tested by fire assay before anything leaves. And here is the first look at what loading actually looks like at real scale. Chutes dump ore straight into an open hold in a continuous brown avalanche. Dust rises with every impact. The barge just sits there and takes it. Man, this is not filling a truck bed with a shovel. Swing over to Dampier in Western Australia, and a Cape-size bulk carrier is doing the exact same math. Ballast water gets pumped out as cargo weight goes in. Trim, list, and hull stress are all balanced hold by hold. Get it wrong, and the ship literally deforms itself out at sea. And when the port is too shallow for the big ships, the loading comes to them. A specialized transshipment barge steams out 8 nautical miles offshore, meets the Cape-sized vessel, and transfers ore in open water with dolphins swimming past the whole operation like nothing unusual is happening. One camera looking straight down into the hold puts the whole industry in perspective. A steady brown stream falls for hours. Behind it, mines, trains, ports, ahead, a steel mill on another continent. Every steel product in your kitchen, garage, and skyline started as a pellet like this. Cars, ships, tanks, bridges, power plants. Same rock, different destinations. Whoa! 1.8 billion years of geology compressed into a few dozen hours of processing. That is the shortcut modern steelmaking pulls off every day. And here is the money shot of the entire iron ore industry. 2 workers in full protective suits tap the furnace, and a river of molten iron pours out at over 2,500 degrees Fahrenheit. This is the second the mine, the port, and the ship all cash their paycheck at once. A newer play on the same idea is direct reduction. A billion-dollar plant in Toledo turns pellets into hot briquetted iron using natural gas. Same product, roughly 25% less greenhouse gas by 2030. Step inside a full integrated steel mill, and the process finally makes sense at scale. Iron ore and coke ride in by rail and freighter. The blast furnace runs 24/7 at around 4,000 degrees Fahrenheit, producing roughly 6,000 tons of molten iron a day. A robotic arm drills out a clay plug and taps the furnace. Molten iron flows into insulated bottle cars, gets railed to the next building, and gets poured into a basic oxygen furnace, along with about 25% scrap. Pure oxygen, over 21,000 cubic feet per minute, burns off carbon and turns the whole batch into steel. Ladles then move to the ladle metallurgy facility, where alloys get added under electric arc reheat to lock in the exact chemistry the customer ordered. Some grades go through a vacuum degasser that pulls carbon down to 0.01%, the stuff car body panels need. Liquid steel then pours into continuous casters, gets cooled by copper molds and water mist, and comes out as an 8-inch thick slab. Slabs get reheated to over 2,300 degrees, hammered down in a roughing mill and stretched out in a 7-stand finishing mill until an 8-inch slab becomes a 4,100-foot ribbon of steel. Watch a slab enter one end and coil out the other in minutes. And the whole point of this video finally lands. And here is what that ribbon actually looks like in motion. Glowing red hot slabs slide across the mill on rollers, get squeezed thinner and thinner between rolling stands and hiss through water sprays that flash into steam clouds. Every pass makes the steel longer, thinner, and stronger. The finish gauge can drop to below 1/10 of an inch, thinner than a coin. The strip travels fast enough that a slab starting as a stubby block can become a coil hundreds of meters long in a couple of minutes. One pellet in the mine, one coil in the mill, 2 years of chain in between. By now, this scene should feel familiar. Ore cars from a mine hundreds of kilometers upstream roll onto an elevated discharge line. Workers in full harness gear signal the engineer to move 3 cars at a time. Bottom gates open, ore falls, gates close, track gets cleaned, next 3 cars roll in. Meanwhile, in another yard, loaders scoop pig iron produced from the same ore stream and poured it into different rail cars, bound for a port terminal downstream. You have seen mines, plants, pipelines, pellet lines, ports, ships, and furnaces. This is one small station in the middle of all of it. Hundreds of millions of tons of iron ore quietly circle the planet every year, and most of it moves through machines nobody outside the industry ever sees. Autonomous trains crossing deserts, slurry pipelines running under forests, Cape-sized vessels loaded 8 miles offshore, blast furnaces tapping molten iron at over 2,500 degrees. And at the end of all of it, a coil of steel showing up in your car door. The conversation the industry keeps having right now is worth watching. Some argue direct reduction and hydrogen-based steelmaking will quietly retire the blast furnace within 25 years. Others say pellets, coke, and the classic route still have decades left. Which side of that call sounds right? Is the blast furnace a relic in the making, or still the workhorse in 2050? Toss your thoughts in the comments. Appreciate you riding the whole chain out. Smash that subscribe if the next heavy industry deep dive sounds like your kind of afternoon. See you. Take care.